Welcome back. In this lesson, we're going to look at what's left over after a star dies. So you're still going to have what would be stars. So if you were to have a regular small mass star, and after it uses all of its fuel, it kind of collapses under its own gravity. So there's not enough thermal energy pushing outward because it's not burning anything, but yet you have lots and lots of stuff there, so the gravity pushes in and it shrinks into what's called a white dwarf. So a small mass star would eventually turn into a white dwarf, and a middle star as well. After it grows to a giant, it's burning and burning, and it's using up all of its fuel, and eventually it collapses, and that collapse, after its collapse, is called a white dwarf. White dwarfs are really, really dense, much denser than any material that's ever been on Earth, because if you remember any of your chemistry, you've got atoms that are surrounded by electrons. So you've got like a little nucleus that has positive and neutral particles in it, and then it's surrounded by clouds of spinning clouds of electrons. Well, the electrons are and the protons are attracted together, but they can't go much further. There is an electrical repulsion there between the various electrons to each other, and they can't get tighter and tighter. And so what's going to happen is that on Earth they only go to a certain distance. But in a star, if you have so much gravity, it's shoving it, you actually have the electrons really, really close to the nucleus. So it's an uncomfortable place, but if you were to have a teaspoon of a white dwarf, it would weigh tons, okay? Even though it's only this big, it would weigh many, many, many thousands of pounds just because of how densely packed that matter is, okay? Whenever the electrons are kind of distorted to where they're going where they don't want to go, this is called degenerate matter. It's degenerated, meaning it's not its full shape. It's a distorted shape. It's also going to get really, really hot. Okay, so a white dwarf is very, very dim, but very, very hot. So on the HR diagram, it would be in the lower left of the HR diagram for that reason. Theorizing, it is possible that can't last forever. You don't have new material being generated, and as it cools, you are going to eventually have what is thought of as a black dwarf, because this material would have to cool, and after it cooled, you wouldn't be able to see it anymore. It wouldn't be producing light anymore, and as such, theorized called a black dwarf. Neutron stars, okay? If you have a very massive star and it burns all of its fuel and it gets bigger and bigger and bigger and eventually becomes a red giant, so huge, okay? So a red giant, if you were to have like Betelgeuse, the level of Jupiter, the orbit of Jupiter would still be within the star of Betelgeuse. That's how big it is, okay? So we're talking ridiculous amounts of size here, ridiculous size. Well then, as soon as it stops burning anything, it doesn't have an outward push due to its thermal energy. All it has is gravity, and all that gravity is just going to collapse on itself. And it collapses on itself so huge, because we've got a ridiculous amount of stuff, and it just falls in on itself. It becomes so massive that the electrons don't just bend, they don't just distort, but they actually go into the nucleus itself. And when you form these electrons together with the protons and neutrons, they become more neutrons. Okay, I'll have to teach you that later. But eventually you've got a change in nuclear material, and so you become neutrons. That's why it's called a neutron star. So you don't have protons and electrons that are repelling each other electrically. They've fused together and turned into neutrons. The force holding them together is so strong that it's actually fusing new material, and that's called a neutron star. If you were to have a teaspoon of a neutron star, okay, it would weigh more than the Earth. Okay, even though it's a teaspoon and the Earth is as big as the Earth, if I were to to take a teaspoon and drop a teaspoon, pour out, I'd have to be very strong, pour out the teaspoon onto the ground, it wouldn't just fall to the earth. The earth would fall up to the blob and pierce itself over and over again like a Swiss cheese, because that teaspoon would weigh more than the earth weighs. Okay, so the teaspoon wouldn't fall. The teaspoon would stay just where it is, and the earth would come up and fall on it and pierce itself on it. So it is beyond compact. Okay, it's actually compact down to where it's the density of the inside of a nucleus. Okay, that's how dense it is. All right. So when the gravitational pull collapses it, the protons and electrons combine to produce neutrons. That's why it's called a neutron star, and it's very, very small and very, very dense. Okay, I think my example was a little more dramatic. The idea of a teaspoon of a neutron star would pierce the Earth thousands of times like a Swiss cheese. This has the idea that if you had a pea-sized sample, it would weigh 100 million tons. Okay, so that's the idea of the entire Earth condensed down to the size of a football field or something like that. That's how dense that it would be. The first one that was discovered was in the 70s, and it's called a pulsar. And what's happening is it is so strong, it's so dense that it spins. Okay, so the sun right now is spinning on its axis, like every 25 days or something like that, it's going to spin on its axis. Well, in the case of a neutron star, it's going to spin, whirring around at very high speeds, and it's going to send out a magnetic field, kind of like a beam. And if you are lined up with that beam, you can detect it. And there are a few pulsars that were found even 50 years ago, and many since, that would allow you to say, okay, there is our first neutron star. And it was theorized as a leftover of an explosion of a supergiant. Some Hubble Space Telescope pictures of some remnants of these supernova explosions, these enormous explosions where the whole star was ripped apart, and now all the leftover is the gases again, so you end up with a nebula again, and lots of energy that is released as well. Now, so we're again in theory, but there was a black hole that was spotted at the center of the Milky Way galaxy, our galaxy. I believe it was last summer, and there was actually a picture taken which made all the papers. But a black hole is even more dense than a neutron star. It is so dense that the light from that star itself can't escape. Okay? Light, even though it is the smallest thing anybody knows of, is still stuff. There is a little bit of stuff. A photon does have some mass. It's almost nothing, but it does have some mass. But if you have so much gravity that mass the light can't even escape, then what you have is called a black hole. It's denser than a neutron star, so dense that even light itself, thought of as an object, cannot escape it. It's so hot, and it emits X-rays and actually sucks in other stars. So it's almost like water going down the bathtub. It's just pulling in. It's so much gravity that anything that gets near it will be sucked into it. It makes for great movies. So this is the classic, the idea that you've got a black hole at the middle of a galaxy, and as you have stars near the center of that galaxy, no matter how big it is, the material from that star falls into the gravity pit of this black hole and is basically sucked into it. And then the energy is emitted as a jet through both sides of the black hole. Who knows if it goes through another portal and all kinds of stuff like sci-fi, but it's pretty dramatic. It's about as dramatic as stuff gets.